Hello, everyone. Let's give it another couple of minutes. See.
Zoom always wants to randomize my audio inputs and outputs, so it takes me a minute to get that unwound. So if you said hi to me when I joined, I didn't hear it, but hi.
Hi, Dan.
I think I have the same problem.
Yeah, just quick check. So do you hear me clearly?
Yep.
Yes,
Yeah.
Rama. Yeah, very well.
And also you see me as well.
Yes.
Yep.
You and a whiteboard behind you. Yeah.
Yeah, perfect. I will apply some background.
No, it's okay. Okay, people are still joining, so let's wait a bit till we stabilize. Okay, I think we can go. Welcome to the attestation SIG meeting. The Google Docs document is at the usual place. Maybe I should copy it onto the chat. Wait a second. But anyways, please stick your name there. And if you want to add notes, you are certainly most welcome. And we'll be eternally grateful. Thank you. Thank you, Keith. Yeah, so this is recorded. Regarding the recordings, yes, I've spoken with Kurt about moving the videos to YouTube as we agreed on the list. And he said it's on his to-do at the moment. So in the next weeks or so, we should be able to get rid of the old school TXT file in favor of, playlist or something on YouTube, which is good. But I'm not sure exactly when. It depends on, the work schedule. Kurt's work schedule. Right, and before moving to the next topic, there are a couple of things about the attested TLS track that I wanted to discuss first. And the first point is that we have a bunch of presentations that we missed apparently. So we seem to have forgotten RATS TLS that was mentioned by Dan on the list, which, if I understand correctly, integrates with Oclum, and so it's quite relevant to us in general. And it's based on SGX. So it should be in the same category as RATLS and the attested TLS for Open Enclave SDK. But it said something about the implementation status, which I didn't grasp correctly. So Dan, could you please expand on what you said in the email regarding
Yeah, so I think the implementation is different in the sense of like it's a different set of code. And I think one of the salient aspects of that is that there is a different abstraction with the underlying SSL libraries. So I think you've got a couple different libraries that you can pick from for that integration that might be different than what's available through RATLS, for example, or through the implementation in the OE SDK.
Okay, cool. Right, so and still talking about this missed presentation, I had a private email with Arto Niemi from Huawei. He told me they have some prototype codes for an attested TLS 1.3, and he asked whether it was possible to present it. And Hans as well from Intel reached out to me just today to point me to the new version of HTTPA. So we seem to have, enough material for another 1 hour, 1 hour and a half worth of presentation, if there is any interest in this. So the problem, the thing is that I don't want this to interfere with the new discussion track. So, and a possibility here that I'm putting forward is that we could schedule a meeting in the same time slot in one of the other Tuesdays. So in between two of the usual meetings, maybe, I don't know. Otherwise, we could postpone these to the end of this track. And
I would tend to think postponing till the end of this track would be good. We can have like a roll up of any updates for attested secure sessions at that point.
Okay, I don't have any strong opinion. I was just voicing this, and so I'm
Yeah,
okay.
I'd say it depends on, do we have a good lineup of talks coming for this current track?
Not yet, but I think it wouldn't be very difficult to, to surround the right people and have at least, say, 4 to 5 meetings worth of presentations.
Okay. Yeah, I think if we've got content ready to go, then we should stick with this, and I agree with both of you that we can kind of come back around to the other TLS like updates after that.
Okay, that's good. That's good.
And then also on secure sessions, last time we had talked about collecting like proposals for follow-up work on the secure sessions.
Absolutely.
How are we managing that?
Yeah, that is the other point that I wanted to understand, whether there are any project proposals in the making that you are aware of, and if so, please reach out, because for example, from my angle, we are working within ARM to make a proposal for a prototype around HANES protocol extensions, which integrates with Verizon, with Parsec, with Embed TLS, and is part extension, part integration, and it's a gigantic thing. But we are still working out the details, and we will probably come with the concrete proposal in a couple of weeks, not earlier than that. But I wanted to know whether other people had something concrete to put forward. For example, Dan, you were pretty positive on the array TLS and the Open Enclave merge, or some kind of harmonization there, right?
Yeah, so I started some internal dialogues within Intel to see if we've got support for doing that. And so I'll need a little bit more time to pull that together, but then I anticipate being able to reach out to folks on the other projects who've presented and see if we do have some interest. So for those of you who are on the call now, if you want to just ping me on Slack or whatever, we can do that parallel as well.
Super.
And
Okay.
then the one that I had in mind was on the STET protocol. It's right now it's done in a way that's fairly use case specific. It was built for that, but it was designed with a more general use in mind, and extracting that out into a more general purpose reusable library is something that I think could be useful.
Fantastic.
Yeah, and I'd like to, especially if we're going to refactor what we have for RATLS and stuff like that, if it makes sense to do that like application layer protocol at the same time, and we come up with something different, that's on the table as far as I'm concerned too.
So Dan, if I understand correctly, you're open to modification to the protocol itself.
Yeah, I think the thing that's pretty straightforward is saying, all right, we've got a few different TLS variants, and we could make just one of those because they were all pretty similar. STET was one abstraction layer higher, I think. So I don't know if it naturally fits in or not, but if it means more people get more value out of it, I'm game for figuring that out.
So you're saying whether or not it could also be merged into the same thing?
Yeah.
Okay, that's interesting. Okay. We can discuss that.
Yeah, we should explore. Cool.
And Tomas, could you say again what the project that you were considering was?
Mine was working with, you remember TLS CWT? Hannes presented a way to make CWTs as first-class credentials in a TLS handshake, like, same as X509 certificate, but different format. And wanted to do something around that. So protocol extensions that integrate that into Embed TLS, and then built on top of that a couple of endpoints that have a Parsec backend and the verifier on both ends being Verizon. Trying to pull together 3 pieces, one of which is now a CCC project, and 2 other things that are in scope, I would say, relevant in general. One is building block, Embed TLS, and the other one is a very similar minded, I would say.
Okay.
similarly scoped project. Right. Okay. So we can. Sorry. Yes, Greg.
Yeah. Not as reaching as big as what other folks have been discussing, and I've certainly taken no specific action. But the one area that seemed like some fairly low-hanging fruit and potentially not a huge project, but potentially having some value, is to standardize a mechanism to encapsulate or encapsulate attestation evidence inside of an X509 certificate.
Absolutely. So Greg, that's why I was asking, so sorry to interrupt, but that's why I was asking Dan whether he's open to protocol modification, because it's exactly what I was thinking. There is this thing could be the object that we factor out from both RATS and the attested TLS in Open Enclave.
But I'm not even thinking about a library that does TLS based on that. I'm just thinking about a standard place to put the evidence, perhaps some standard libraries to set and retrieve the evidence, and what you do with it, whether you establish a TLS secure channel or not, is kind of secondary, because we have some scenarios where we don't use that to establish an attested TLS channel. So even that smaller building block is useful for some of the things going on in my area.
Yeah, but okay. I think we can push it a step forward and try and standardize exactly the format, right? So grab a node and decide how the extension looks like effectively. And so, we find a container, and so we can build the library once and for all, because we assume that the syntax is common.
Yeah. I guess maybe what you're saying, which makes some sense, is if part of standardizing, if part of trying to get more harmony in the attested TLS scenario, as a byproduct of that, we formalize and standardize the packaging of the attestation evidence in the X509 certificate, that then itself could be a reusable component.
Yeah.
Sounds great to me.
Cool. Okay, so if we have exhausted this, we can move to the new topic, which is the attestation formats. So in the next, I don't know, we haven't bound this track, but I think we could go for 4 or 5 meetings at least. We'll be looking at the semantics and syntax and conveyance of what the RATS architecture calls the conceptual messages. So attestation evidence from the attester, the attestation results from the verifier, as well as endorsements and ref values from the supply chain. And I think the primary objective here is we create some sort of shared knowledge, right? Because not everyone knows everything, but each of us knows a little something that they can share with the community. So if you think you have knowledge on a specific format, say for example EAT or TPM or SEV or SGDICE or whatever, step up, grab a presentation slot from one of the next meetings agendas and come and talk to us about that. So from my point of view, with my Verizon and HiATF RATS on, and I'm sure everyone has his own angle, but what I want from this discussion, I want to get a better understanding of the semantic layer across the different technologies. I'm not very much interested in the serialization details, but the semantics for me is important, because I need to understand what are the emerging patterns and the commonalities that I can leverage to design an attestation result format that I can give to a relying party, and the relying party can take the useful semantics in a simple and homogeneous way, and it can build its appraisal policy on top of that. And another thing that I'd really like to see in this discussion is to get a better understanding on the conveyance methods that we are using in various ecosystems. And so any existing APIs, that would be very, very, very important for me. But this is my private angle, so I haven't thought of any other high level or more specific objectives. So if you have thought about this, please state your wish. For example, Dan has done that on the mailing list. Thank you, Dan. And he said, let's talk about it. Let's talk about tokens, and in particular, if I understand correctly, Dan, you wanted to have the Azure point of view on this because they are using it and they have operational experience with that. So that sounds exceptionally good for me. So maybe Greg is the one here to pester for that. But
yeah, I was trying to shove Greg in front of the bus there. I wasn't quite sure if he was going for it or not.
Yeah, I think you picked the right person, and I'm certainly willing to do it. I probably can't be ready in 2 weeks, but probably in 4 weeks I could be ready to. It's just kind of learning in the trenches how we've tried to provide EAT tokens from the Azure Attestation Service and kind of where we stand, and some of the challenges and things like that. But I'd be happy to. But
splendid. So I've spoken with Simon Frost about this, and I think we can bring our own angles on it, both from a standardization point of view. So maybe, for example, describing the thing in general terms, and then from an implementation point of view as well, because we have implemented it in a couple of things, in more than a couple of things in our software. So maybe we can present this, Greg, we can do that split thing, or I don't know, we can do an introduction to the thing, or we can do a complement, whatever. But I'm sure we can work out a thing on it that makes sense for everyone.
Yeah, if there's multiple parties that are probably going to do something EAT revolving around EAT, perhaps just discuss offline and see what kind of makes sense, combined or independent presentations.
Okay, so let's kick off something offline, or maybe on the Slack channel. I don't know, whatever.
Yeah, either works.
Okay.
Yeah, and then later this week I'll be talking to some of the leaders from Intel's Project Amber. So Intel announced an attestation service at our Vision Forum. It was a week or 2 weeks ago. So want to see if they've got some content that fits within this for what you do with the attestation artifacts.
Splendid. That would be great. Okay, so we seem to have at least 2-3 pieces that can become more concrete in the next few days. Anyway, but we can start now, and the first volunteer for this is Usama, and who I'd like to thank for putting his name down. He will be talking about TDX, if I understand correctly. So Usama, please, grab the mic and go ahead with your presentation. Do you prefer question to come at the end or in a more interactive style?
I will be preferring interactive, so that it's not like lecture. So you are very welcome to interrupt me anytime within the presentation.
Thanks very much. Okay, go ahead.
Okay, so just please confirm me that you see the slides, and then I'll start.
Yeah, we see the slides.
Okay, perfect. So thank you very much and for this opportunity. And I want to talk about attestation in Intel TDX with a focus on the formats, as is the current line of discussion. And those who don't know me, so I'm a research associate at the chair of systems engineering at TU Dresden. And the outline that I have drawn for today's talk is that I will give an overview of TDX, just a brief one, just to get everyone on the same page. What we trust, what TD trusts, what trust domain is supposed to trust, and what not. And then I have divided it into 2 main parts. From the discussion, I have just learned that more interesting is the attestation results. However, our focus so far has been on the code generation. So that's what I will be describing in more detail. And then I will also, the link between the 2, generation and verification, is the protocol in between, which is how the signatures are done and how the signature chain is built. So I will be describing that and building the chain between the generation and the verification.
Osama, sorry to interrupt. Is the
Yeah,
meeting
yeah.
Is the meeting recorded?
I assume that is recorded.
Okay, please go ahead then. Thanks.
Okay. So the things that TD is supposed to trust are listed here from the Intel's documentation. Basically, the Intel TDX module, the Intel ACM module, to which we do not find much details. So what exactly or how exactly it operates. So this is really a bit vague, in my opinion. TD coating enclave, if you are familiar with SGX, is analogous to SGX coating enclave, which has the key with which the signatures will be done, and Intel CPU hardware that we need to trust. Somehow I do not see explicitly being mentioned provisioning certification enclave, but that is one of the questions that I have. How does it build trust with the provisioning certification enclave if it is not explicitly being trusted by the trust domain? So I will describe a bit about the chain, and then maybe somebody from Intel has some points on that or some ideas. So there are many people from ITF, they know this, so that this is related to the background check topology, where somehow this TD and the TD coating enclave in general are forming the attester. And the definition of attester itself, in my opinion, is as defined by IETF is a bit vague. Like I could take, or I could consider, let's say, TD plus TD coating enclave as attester. I could also add VMM. I still have definition of attester being satisfied. I could add Intel TDX module. I could add CPU hardware. I could keep adding the things. It still kind of satisfies because it only says we have one attesting environment and one measuring environment or something like that. I think is the terminology. Anyway, the idea is that some parts of this thing are the attester, and challenger or the relying party is getting some evidence. And then there is this attestation verification, which is the attester, the verifier, with which it is going to get the verification result. So it's forming the background check topology. And I will describe a bit about, so this is the general overview of how things, the step-by-step formation of the code. So this part is forming the evidence, which in the case of Intel SGX and TDX is called the code. And then this part is forming the verification, where this relying party and the verifier is giving the attestation results. Okay, so as I said, I have divided into two parts, the code generation and verification. And firstly, about code generation. I described a little bit, so that was supposed to be just an overview of what the entities are and how do they process. Here, the idea is that I have two of the entities here from Intel's documentation, that are the trust domain and the TD coating enclave, analogous to the SGX coating enclave. It takes VM data or a public part of the key, which it has, which the trust domain has, and some measurements from TDCS. It is analogous again to SGX, SCCS, SGX enclave control structure. In this case, it's TD control structure, where there are some measurements which it is taking, measurements of the TD, which is actually taken from the TDX module. And then these data are then put into the part of the TD report, which is like SGX report. And then this is mapped using the MAC key, which is available only to the CPU. And if both of them are on the same CPU, then this CPU can then verify that on receiving this MAC report, that this was generated using the same MAC key, which is available only to the CPU, which is not shown here. So there is another figure in detail. So this is just supposed to give an overview of what happens, how this is protected within the within the platform, so to say. And then when we are going outside the platform, we have to, so this key, then this MAC key will no longer be available to the relying party. And then one needs to do the signatures with which it can then verify. And this signature is done using the, which is somehow written here as a code key, which is the attestation key. And then the public part of the key will be put inside this code, which is Intel's way of doing that. And then this can be verified then using this, verifying the chain that it belongs to the same platform. So I will add a bit of details here. So the last slide actually described trust domain and TD quoting enclave. So these are the two entities. I add here the VMM and CPU and SIEM representing the TDX module, which was in the first diagram of the overview or generally how it works. Okay, and again from the first figure, if you remember, so there was a data or public key that was put into the report, and the second arrow was EDCS. So there are some measurements taken from the TDCS put into this report. These measurements are for the trust domain. I will describe what these measurements are. And then the idea here is that the CPU, as I said, will have only the CPU will have access to this MAC key, and then the SIEM representing the PDX module will, these measurements will be added inside this so-called SIEM report. And this is mapped using this MAC key. And then this MAC report will be, this TD measurements or TD info is then added to it, called as the TD report. And then this TD report is passed via this untrusted VMM over to the TD quoting enclave. And then the TD quoting enclave, as I said, can then verify this because it has access to the MAC key, and it can verify that the MAC is the same, or otherwise the data has been tampered. And that's the final step. And then it's signed using this attestation key. And then the quote itself will contain the public part of this, with which it can, the relying party can then verify. Okay, so coming a bit towards the formats of the reports, or all the structures which are involved. The two of them are, the SIEM report is basically representing this part, which is the MAC part of the created using the SIEM report instruction. And here the idea is that we have two main structures inside this SIEM report. And one of them is TCBI, which is representing the measurements and configuration of TDX module, which, if you remember, was measuring the TD, the trust domain. And there is one generic MAC structure which is containing all the data, and this all data appended with the MAC, which is created over all of this data. And important thing to note here is that it's also containing the hash of this structure. So all of these measurements, as well as configurations, such as the measurement of TDX module, its SVN, and valid field representing whether these two fields are valid or not, and some reserved fields which might be used in the future. So this hash is included within this, and that's protecting these measurements and the configurations of the TDX module. And then the overall protection is done via this MAC, which is created using this key, which is only available to the CPU. Okay, so the code generation part, summing it up, I already described a bit that this is being protected via a MAC. So just a simplified view of the overall thing. The TD report, I just described this RMS and TCBI. The TD report itself consists of these four fields. RMS containing the MAC, this is what I just described. And TCBI representing the TCB information, and it is its hash is contained inside this. These two combined together are called SIEM report. So this is just SIEM report appended with the TD information. And these are some reserved fields again. So this TD information the hash again is included within this report. So this is the main part which is protecting all of this information. I mean, this part as well as this part are both hashed and then put together inside this and then protected via the MAC key, which is only available to the CPU. Okay, a bit about a bit of details, and I wanted to describe here all the structures which are used in one go. The TD report, which is the structure containing all of the measurements and configurations and everything, both related to the TDX module as well as to the trust domain, are represented here. And this, as I said, is containing the MAC, which is overall protecting everything else, including the TDX module measurements, SVN, and so on, as well as the trust domain measurements. And important thing here to note is this MRTD, the static measurement register, which is the load time measurement, which is analogous to SGX, and it also has 4 runtime measurement registers. They are basically measuring at the runtime what is being loaded, and that makes it different from SGX. And because it's a complete VM, so everything we need to measure at each time. And it's just like PCR, that the measurement is appended to the previous measurement, and it's functioning just like PCR. So each of them is can be thought of like a PCR register in terms of working. I believe there is one more field added very recently, which I do not have here, in between the measurements and the result, which is related to service TD. But anyway, so this is the overall idea of the structures that are contained inside this. So from the formats perspective, it's important that how am I going to know that which of these field is which one? So this has each of these structures or substructures have a specific field size, and the overall TD report is 1024 bytes. And so each of them has fixed size, so one can know that, okay, so this is at this specific place there should be this measurement register, and then one can extract out and compare with the required measurements. And from the cryptographic perspective, again, the protection is done via this MAC, which will be replaced by the signatures. Okay, so one thing which is still not clear to me is the format of the TD port, which will be the final structure which will be sent over to the relying party. From Intel's documentation, one thing which was the only part in my understanding which describes this code is only this figure. So there is no other document to my knowledge, please correct me if I'm wrong, so that describes about the trust domain code, and this is lacking some of the fields that we expect should be there. So there is no clear description of the final structure of code which is there. So in the paper we have we described it and sent to Intel also, however did not make to the final specifications, which are now the most recent ones. Somehow some coloring has been done, but however the code is still like containing the same fields. There has been some update, as I said, service TD hash is included, but still it's not clear like what is exactly the thing inside the code. What is the structure? What exactly is it containing? This is only giving an overview. And it's not very clear that what exactly is going to be the format of the final code that will be sent over to the relying party. Okay, so the link between the generation and the verification, as I said.
Sorry to interrupt you. The Yogesh wants to ask a question, probably.
Yeah. Thanks, Thomas. Yeah. So you have explained a lot in detail about the code, but do you have a kind of a similar picture of the kind of supply chain? What elements would a verifier need it from the supply chain equivalent elements so that can matching verification be correctly done? Are you going to cover that as well, or?
I guess you're talking about the verification part, which I will describe in a few minutes.
Okay, I mean, I understand my main question was, are you going to talk about the reference values which would be required to verify such kind of codes? Okay, thanks.
Exactly. Yeah.
Okay.
Not in so much detail, but I will touch upon it at least. And I'm happy to discuss offline if you have question, or of course, I think we will have some time. Or please interrupt me when I'm wrong. When I describe that, that's in the verification part.
I might have to leave in 15 minutes, but I will definitely discuss offline and review the rest of the presentation. But that's fine. Thank you, Osama.
Yeah. About the protocol part, it's really simple. I have described already that the local attestation part that is within the platform is done via this MAC, which is of course metric cryptography, and for the remote party, which will not have access to the key which is used for MAC, the MAC key, and then it needs some other way, which is using this digital signatures that it can then send over the public part, and it can then verify that the signatures were created using this part. Okay, so for the protocol, it's important that we define what are the key roles inside the protocol. And the trust domain, of course, which is the party which is going to, which is to be verified and to build the secure channel between the two. And then the TDX module, which measures the trust domain. And it is trusted. CPU hardware, which has a MAC key and is trusted. TD coating enclave, which is also trusted, and it's going to perform the signatures using the coating key. And the TD provisioning certification enclave, which is going to sign this, this TD coating enclave, which I will describe in the verification part. And the challenger, or in other words, this is the verifying relying party, that the relying party is merged with the verifier. So together, this being considered as the inside this protocol. Okay, so the protocol is like this, that we have a challenger here, and all the entities that I described, except the provisioning certification enclave, which we have not, in the last part, which we had not included, it's a work in progress. We are now including the provisioning certification enclave to have the full chain of trust, and to then analyze formally, which is a different topic, which I do not touch upon here. But the idea is that this is still missing one entity, which is this provisioning certification enclave. The reason behind this was that the protocol that PCE and QE run inside is not very clear, and the provisioning part of the PCE itself is not clear, that how is it provisioned. And that's why in the initial work, the idea was to assume that this is already provided with an attestation key, and it has a certificate which is then used for verification. Okay, so from this part till this part, the verification is the local attestation part. And I won't go into the details of this process unless someone is interested in specific things. So the idea is that challenger just sends an attestation request to guest TD, and just like report data in SGX, we have here our data, inside which it can put its public part of the key, or some specific data which it wants to share. And then it gets some measurement from TDCS, computers, hash, and so on. So it creates a report, same report, which I explained, adds these TDI, the trust domain information, and which is called the TD report, passes over via the VMM, and then the coating enclave is going to check the hashes which were inside this report, and ask the CPU to verify the MAC over this, and then it will get the verification results. When both of these checks pass, it signs the code, it signs this TD report, except the MAC to form the code. As I said, the exact format of the code is not very clear. There is only one figure which I showed previously, and then it's sent over to the challenger. Okay, so this is the part about the verification, and there are different steps here included in the verification part. One of them is about the certs and the certificate revocation lists, and it is then going to be from the signature chain. One part of it is the signature chain from the court, which is the final thing that or the evidence in terms of IETF that the challenger or the relying party is going to get up to the Intel's root certificate. And secondly, another step is to perform the key revocation check, that any key, none of the keys inside this certificate revocation, inside this whole signature chain is revoked. And then we have the reference list, which was just asked, reference values. And here, Intel TDX architecture verifies three main things. One of them being the quoting enclave is from a suitable source and is up to date, meaning that the quoting enclave measurement is as expected, and its SVN is greater than or equal to the minimum threshold that was expected. And then the second reference value is the TCB, meaning that all the hardware SVNs are as expected, and also the PCE ISV SVN is as expected. And finally, this measurement identities, which I described that the TD has two types of measurements inside the TD report. One is the MRTD is, I guess this is the static measurement. Yeah, so this is the static measurement, which is done at the load time. And these are the 4 RTMR, the runtime measurement registers, which are done at the runtime. So it checks against the expected values or the golden values that they are as expected. Okay, so does this answer your question? If you are still here.
Yes, I'm here. Yeah, thanks.
Okay, welcome.
It does shed some light on what exactly is provisioned in a verifier to do the matching in verification. Yeah, thanks.
Okay, great. Right, so I now want to discuss a little bit about in more detail about the certs and CRLs. Not much about CRLs, but more about the certs. Basically, how is the inside the overall architecture, what is the verification flow? And it's a nice figure from Intel's documentation. However, it's not very accurate, I will describe. So the migration TD, which is the latest version 1.5 of Intel TDX documentation, where this migration stuff has been added, but the overall flow is the same as normal. So the verification chain as described here is supposed to verify the PCK certificate, which somehow they have written that it's Intel root key signed, which is not, in my understanding, or at least is not what other documents describe. I have a figure in the next slide, so I will describe why I have this opinion. Then this is going to verify the attestation key certificate, which is signed using the key which the PCK, the provisioning certification enclave has. And then this attestation key certificate is then we verify the code. And finally, inside the code, we have the measurements, which I just described, the two measurements against the golden values, which are this runtime and the load time values. And yeah, I described this point. So why I say that it's not directly signed. So this is another Intel's documentation, which is describing the PCK certificate chain. And the root certificate is not directly signing the PCK certificate. However, the hierarchy is like this, that it's going to be either the PCK processor CS certificate or the platform CS certificate. And then this certificate has this PCK certificate, which is the case that whether this is, we are dealing with specific type of a platform, which I will describe in a coming slide. And then they also have this CRLs corresponding to that, from which we can check whether the keys are revoked or not. Okay, and the signature chain here corresponding to this is like this. Again, just a recap, that PCK certificate is Intel signed but not root key signed. And this attestation key certificate is then signed by PCK provisioning certification enclave key. And then the code is signed using this attestation key. So combining the two figures, I have a summary in the next slide, which is exactly describing exactly what are the entities shown as the ovals, and here the certificates which are available to these, which are corresponding to these entities. So this is this root CA of Intel. It has this root CA key, which I just name it randomly, just to make the chain and to show what exactly is the process of verification. And it is, of course, so it is a root cert, so it is self-signed, and it contains itself, the public key corresponding to this key is contained inside this certificate. And then with this private, so all of these are here, the private parts of the keys. And with this private key, it's going to sign the certificate for PCK for this entity, which is the PCK processor CA. And this certificate contains the public part of this certificate authority. And then this is going to sign with this private part, the PCK certificate. And it will contain the public part of this key, which is again the private key, which is available to this provisioning certification enclave. And this I really believe that is not clear to many people. Then how this chain is completed, and that's why I try to summarize it here. And all of these certificates are X509 certificates using this RFC 5280. And then there are these custom formats for these two certificates. And we struggled a bit to find out what exactly this AK certificate is. I will describe in the next slide. Of course, it's our understanding, it's so far. And feel free to correct me if I'm wrong. So this PCE then signs the certificate for using its private key PCK, the certificate for this TD coating enclave, which Intel names as the AK certificate, which is I describe in the next slide. And then this TD coating enclave is going to sign this structure, which is the final coat. And again, it contains the public part of this AK, and then this contains the public part of this TD key, which I call it. So this is then going to be sent over to the relying party with which it can establish that channel. Okay, so and one thing to our amazement was that this AK certificate is itself contained within the code, and I'm now going to show what exactly this is. Not exactly, or what exactly we interpret from this. So inside the code of there is this part which we think is being referred to as the AK certificate, which is containing the public part of the key of the attestation key. And so I have this simplified representation of what the certificate is. Like, this is public key, its identity, it's going to bind it using a certificate signatures using the private key of the certificate authority. And if you recall this figure, so the certificate authority for this coating enclave is actually this provisioning certification enclave. And its private key is this PCK. It's going to sign with this PCK the certificate for the attestation key for this coating enclave. And so what happens is that this is the attestation key public part, and the hash of this is then placed inside this R data field, the report data. And this report data is then part of this coating enclave report, and hash is taken, and then the signatures are done using this PCK, which is the key for of the certificate authority, exactly this part. And then these signatures are appended to this part, and this is forming a kind of a structure which is being referred to as the attestation key certificate. And just a note that because we are using the hash, and that's why it's signature with appendix and not signature with message recovery, which is the other type from where we can recover from the signatures itself the data. So it's being appended here. That's why we need to send it along. And yeah, feel free to correct me if I'm wrong. So this is so far, to the best of my understanding, the thing which is being referred to as the attestation key certificate. We do not find any description of what exactly it is. And yeah, I think that this is all that I have. I have some further readings, and if somebody is interested in having a look or digging it in more detail. Thank you again for this opportunity, and I'm happy to take, I think I have still a few minutes if you have any questions.
Thank you, Zama. Thank you very much. I think Eric had a question a while ago.
Sure.
Eric, are you still there? No?
Sorry, there I are. I was trying to find a way to get off mute. I found off mute. Okay, the question really was earlier when you talked about the registers that are made as part of the quote. And I was wondering if they were fully application driven. And the reason for that is, how do you make sure that only things that you want can touch the registers, as well as knowing that you have your own local definitions of the register meanings? And I just wanted to know a little bit more about what the requirements or container, or the security measures for the adding to the measure registry would be.
Okay, so are you specifically talking about the measurements which are for this TD? I mean, this static measurement register and
that second one right there, the second one you're doing there, yes.
Yeah, this one. So measurement, the runtime ones, right?
Yes.
Okay, so as far as Intel describes, or as far as I know, the thing is that it's doing a measurement just like PCR. It's doing the measurement and then extending it. But maybe someone from Intel can provide further description to it.
And before they answer, I just want to add one thing. I'd like to know what the protections are to make sure only that enclave can touch that registry, or whether that's unprotected. Like other people can poison it. That's the question. Can other apps that are outside that enclave poison that measurement?
Yeah. I totally understand your question, but unfortunately, I don't have much knowledge to it. So maybe Dan can provide something.
Yeah. Yeah. So Mohammed had it correct. It's basically like extending TPM PCRs. You can only extend them. You can't write values directly to them. And then the access controls around them are described in one of the reference documents, but it's basically that for the runtime measurement registers, those like the bottom ones, I think we prescribe as the TDX module gets to control the lower ones, and then the upper ones are left to the operating system to control.
So there isn't a application level or TDX level protection for the registers? So they are only accessible through the SIEM instructions, I believe, but the like the kernel, for example, would have access to extend. I don't remember if it's just the topmost of those 4 runtime measurement registers, or if it's the top 2, but it's something like that. All right.
I know with TPM PCRs, at least in our opinion, to make them useful, you have to have an event log in order to know what was extended into the PCRs. I think that would also come into play here to help, if anybody did extend something extra into the RTMR, it wouldn't really matter if you could just see what was extended and only pay attention to the events you want. Is there a standardized kind of event log for the RTMRs that would be provided along with the quote, or how is that dealt with? Or is it completely application, like if it wants an event log, it needs to do it itself?
I think it's more that if people want to treat it like a TPM, they can and use the event log mechanisms that are available from that ecosystem. But there's nothing that's like at the hardware level that we restrict exactly how those uppermost runtime measurements are used.
Okay.
Okay, if there are no further questions, I think we can wrap up. Thank you, Zama. It was fantastic. Great
Yeah,
representation.
welcome. Yeah.
Yeah, thanks for digging through our docs. And,
Making sense of a lot of pages, I suppose.
Yeah. So maybe if there are no further questions, I have a quick question just to recap. Like the two things that I still wonder are like, what exactly is the format of the TD code? I think I described it somewhere. So maybe if somebody has more information on that. And the second thing is, how would you say, maybe this is a more question to the ITF guys, like what would you say in this figure is the attester? Because as I described, like you keep putting everything into this and this will still satisfy the definition of the attester. Starting from a very minimum of, let's say, guest TD plus TD coating enclave, you keep on all the entities, it will still be satisfying the definition of the attester. So maybe if somebody has some opinion on this.
I think Dave and Ned had been discussing this on the chat, and so I will leave them.
So the ITF, RAT's architecture introduces the terminology attesting environments and target environments within the attester. So there's a the expectation is that you can decompose the attester into different environments. There could be layered attesting environments within the attester, and where there could be separate evidence produced by each layer. And so I think some folks are trying to apply that layering abstraction to the architecture here to understand, which attesting environments have keys, which ones don't, and kind of the whole relationship there. But generally, the QE is its own attesting environment. It has a key. The other environments have measurements but don't have keys. But using the hardware instructions to move the measurements around, that the QE is able to obtain them and then put a signature over them. But the QE that's signing them may not be the attesting environment that's collecting the measurements in the first place. That's maybe the biggest difference from what you might see in what's represented in the RATS architecture.
Yeah,
so the QE is the attester.
Yeah, please go ahead.
QE is the attesting environment that has a key that is that a remote verifier would be able to directly validate.
Yeah, I just wanted to add, it's clear to me that this is the attesting environment and this is the how do you call it, target environment.
Environment, yeah.
Yeah, so this is kind of clear to me, but it says that it has at least 1 and 1. So this constitutes itself by definition the attester definition. And my idea was that it says only it limits the boundary from the lower side, from upper side, like I can keep adding all the stuff and still it will be satisfying the definition.
Yeah, the point I was making is that the target environment, the guest TD, the measurement is not obtained by the QE. That's actually obtained by the Intel hardware. And then the QE just signs what the hardware tells it.
Yeah. So you are saying that CPU hardware should also be a part of the attester, right?
Right. It's the root of trust. So it's a part of the attesting, and it's a part of the attester, but it's a layer beneath the QE, if you will. And so the trust in the CPU hardware is based on the platform certificate as an endorsement. And the PCK is in the cert chain for the QE.
So you kind of, verifier has to walk the chain all the way back to the root of trust key, PCK, and then back to the Intel root in order to trust the QE key.
Yeah, on similar lines, the TDX module is also going to provide the measurements. So I would assume
Yeah,
that would
so
also be then part of
right. The TDX module is in the trust domain, and so that a hash of that is included in the quote.
Yeah.
But we're not relying on it for signing anything or for collecting measurements of anything.
So I think Ned's answers are great. And so a suggestion to any of the co-chairs that are still on, Keith, Thomas, et cetera, this notion of saying, how do you map vendor-specific terminology to RATS terminology is something that would be very useful to write down or have the industry written down, whether it's in this SIG or at the IETF or on a vendor website or whatever. Right, you could ask the same questions about SGX, TDX, Trust Zone, Keystone, et cetera. Right, what's the attesting environment? What's the target environment? What's the endorsement? What are the reference values, and so on? If there was a way to collect these, that might be another valuable effort for this community to do.
Yeah, I agree. Pencil this down.
Yeah, great. Thanks.
Okay, thanks. Thank you very much. And we can wrap it up, and we need to decide the chair for the next round. So,
Do we have any additional talks lined up or being discussed for next time?
I think we can put forward one on EAT, and there was, but we need to talk, me and you, Greg, about how to split the work. If you want to do the same, and if you want to do that next time.
Yeah, my schedule doesn't allow next time. I can do two out from here.
Okay,
but,
so I can do EAT and PSA.
Okay. Sounds good to me.
Okay. And who's chairing?
I'll be out next week. So
yeah, I can chair.
Okay, excellent.
So it sounds like it's going to be just turn the reins over to you.
Right.
But sure.
Nice. Okay, thank you very much. We're sorted.
Right.
Bye, guys.
All right, take care.
Thank you.
Bye.
Bye-bye.
Bye.